Take off mask. Sorry, running into a little bit. Hello? I'm not. What about now? Excellent. Okay. Well, that was interesting. So first off, I'd like to thank the organizers for inviting me to talk and let me tell you about the work we're doing at Atom Computing with optically trapped atomic qubits. Let me first tell you a little bit of kind of pitch for Atom Computing and what we are. And then from there, we can actually talk about the science we're doing and the development. So Atom Computing is a pretty new startup. We were founded in 2018 by myself and, 2018 by myself and Jonathan King. We have one office in Berkeley, and we're now open to second, way off to the east here. Our goal is to develop neutral atoms trapped in light as a highly stable, externally accessible platform for quantum computing. We're pursuing gate-based things, and we're focused on achieving capabilities of qubit numbers compatible with known error correction schemes. And this is what really large numbers of qubits. Now, the question, of course, is why do quantum computing at a start? And I think there's really only one answer, and it's just a mission computing, and it's to create a useful quantum computer. And there's everyone at this company is kind of fully devoted. Computing is made up of people who are doing software, applications, control systems, business and ops, and quantum engineering. Every one of those people in those categories doing software, design aids and monitoring, job submission, and more. And they're doing it for building a quantum computer. If you have an issue, you go and talk to someone in software, and they help you actually solve your issue so that you can get your projects done. Investigates near-term use cases and explores error-correcting schemes, again, in support of building a quantum computer. I see, I'm probably going to repeat this a few times. And control systems build custom unified control systems. These are capable of feedback so that we can actually take information from the atoms, play new pulses on the atoms, and we can do that also and deploy those systems so that they're not just a mangle of wires. Business ops, people management, infrastructure, everything in support of a quantum computer. And of course, quantum engineering, you have to build, and you have to build increasingly complex. The reason why I think this is so key is my own experience at other companies. I used to work at a company that made microprocessors. Something that was, which is I talked to a stranger who I'd never met before. And they were just flabbergasted, worked inside a fab. revenue stream, everything is about building microprocessors. And they had worked there for a few years. And they never met someone who goes into a fab. This is very, very different, where every is completely devoted to this problem with your project. If you need more money for a project, anything like that, you can go ask someone for help and they will. Now, you also get to do a few fun things that you don't necessarily get to do in academia, which is that larger teams just lead to building a whole bunch of fun toys. Whether that's very efficient instruction set, arbitrary waveform generators for fast feedback so that we can actually make quantum error correction a reality, or it's scalable control systems so that you can actually have a whole lot of controlled with a very, very few numbers of components. In addition to this, you can automatic calibration, database backed programmable sequence, and so on and so forth. So that from there, I'll start talking about neutral atoms. Obviously, we're interested in building a quantum computer, and lots of companies, lots and lots of people are trying to do that right now. Significant investment, both in superconducting qubits, with IBM and others. Investment. There's many, but they all kind of have common goals, and those common goals are, of course, high quality individual qubits, scalable qubit design, and a universal gate. Obviously, there's other people working on annealers, quantum simulators, coherent icing machines, and things like that, but we're going to do that today. So why are we working with neutral atoms? There's been kind of a revolution in neutral atoms recently in the last few years, and it really comes to these three key points. Many groups now around the world have shown trapped atom coherence time above 10 seconds. So being able to write a gate to your atoms, wait 10 seconds, write another gate, and have almost nearly perfect contrast in some of these. People have now actuated 1 qubit gates at crazy timescales, whether that's a single pulse laser or down to like millisecond timescales. Scalable design, optically trapped systems are quite nice. Every time you want another qubit, if you have enough laser power, just add another spot of light, and you're probably going to figure out a way to get a qubit to go there. In addition to that, people in the last few years have really rearrangement and this movement of atoms over a variety of length scales, whether that's tens of centimeters or just a few microns. And what's perhaps more important that got done in the last 10 or so years is low atom loss imaging. So being able to reuse those atoms again and again and again. Run a circuit, take a measurement from your atoms, and just use them again and again. When I was a grad student, I didn't do anything like that. We destroyed all our atoms every time we wanted to read them. And finally, there's been a huge amount of work in just actually performing a universal gate set with neutral atoms. There's been demonstrated large-scale entanglement with like tens of qubits. There's starting to be very good gate-based entanglement for actual gates, whether that's 97% or the hints of going beyond 2 nines in Caltech. And finally, there's this intrinsically high interaction strength with this very, very large on-off ratio. You can turn on something with tens of megahertz or interaction and turn it off very, very quickly. And when it's not interacting, it is very much not interacting. Okay, so that's why neutral atoms. Let's talk about how you actually make neutral atoms. Many of the people here know this already, but I thought I would add one slide. We start off with a Magneto-Optical Trap. Magneto-Optical Trap won the Nobel Prize in 1997. You start with atoms. You're going to bounce photons off those atoms to slow them down. You'll use Doppler shifts to make sure you're actually slowing down atoms when you do it. The idea that got the Nobel Prize was to add a spatially selective scattering, so a gradient field, such that you trap the atoms in one position. Now, one of these is from the Nobel Prize website, and one of them is from Wikipedia. I don't know if you can guess which one it is, but as far as I can tell, I would like the one on the right the most. So how do we do this in the system we have in Berkeley? Well, I'll talk about later on in the talk, but in actuality, it doesn't really matter what we use. We heat the strontium up in an effusive oven. Atoms flow down that oven, down a tube called a Zeeman slower, which uses that Doppler trick and the spatially selective gradient to slow the atoms down and eventually trap them in a 3D magneto-optical trap. This image is from my graduate student work. but it looks about like that in Berkeley as well. Okay, so now we can do this trick actually multiple times in Strontium. We get the atoms from hundreds and hundreds of Kelvin all the way down to a microkelvin and on the order of about 100 milliseconds. We have clouds of hundreds of thousands to millions of atoms at a microkelvin. But now the question is, how do you get down to actually single quanta, single qubits? We use a trick called a dipole trap. We take a laser beam, we put it in objective, and we focus it very, very tight in the cell. We overlap that with the MOT, load many, many atoms into that cell, and then do a trick with light-assisted collisions, or sometimes we think it's photo association, depending on the day and who you ask at atom computing, they'll tell you two different things. But we add light in, which performs an operation which either creates a pair of atoms or just kicks out pairs of atoms, and we get 1 or 0 atoms in the trap. How do you actually go from single atoms with a single dipole trap to many, many atoms? You can potentially scale this up, as people have now done, above 256, but you essentially send many to the objective. Obviously, no one really wants to create many, many beam systems. So instead, you could use a spatial light modulator, in this case, spatial light modulator. So it's a soft trapping environment, which means if one day we want to trap at 4 microns, we can trap at 4 microns. Not even one day. If 2 seconds later, we want to trap at 3.5 microns, we just do that. Similarly, if we want to trap in a square lattice, we do that one day. If we want to trap in a hexagonal lattice, we do that the next day. And we reprogram this thing all the time. You can do very, very arbitrary patterns, both in 2D as well as 3D. We're focused mostly on 2D at the moment. And of course, because it's so arbitrary, you can make your own logo or something with spots. In addition to this, spatial light modulators offer another nice feature, which is they get a ton of light that you actually wanted for the trap into the pattern. And you can actually perform in situ wavefront correction. So you can look at your trap, you can measure how you actually are trapping the atoms, and then you can throw this into an optimizer or ask someone to optimize it for you or whatever, and you can actually make your trap tighter and correct for optical aberrations elsewhere in the system. When we first did this, we started with 87 Strontium. This is Stan Kunda, McDonald, Brian Lester, another Jillian. Essentially, it's very easy. Actually, just look where you created those spots of light. And as long as you've set up your lasers correctly, you'll start loading single atoms. I think this is from the first night where we actually started getting atoms and we said, oh, wow, look at all that, how easy that was. Okay, so how do we actually get to a large array of neutral atoms? Because at the end of the day, the reason why we wanted to do this wasn't just we wanted to collect 2 atoms or 3 atoms or 20 atoms. We wanted to collect more. So again, we want to correct this many, many spots of light. We get very, very good at imaging them. We play around with how we actually do that imaging. And it turns out imaging is one of the key factors of how you actually choose your trapping wavelengths and choose your system. And you actually, as you go, you start to learn how to not just image them in general and see if an atom's there, but keep it around. So you go from a scenario where you can constantly just fill site after site after site to something where you can just sit there and take pictures of the same atoms again and again and again. But how do you actually guarantee that tweezer sites are occupied and ready for computation? No one really wants to figure out how to compile a circuit down to that random assortment of filling for neutral atoms. There's been tons of work in academia on this. And 3 methods I would say have kind of popped up from across the world. There's dynamic SLM patterns, which was done by Jai Wukan. I don't know if others are doing that as well. But this allows you to actually move many atoms at the same time. Actually, the lead author on this now works at Atom. And he showed us some funny tricks about how you can actually use dynamic SLMs. The nice thing about this is, again, it's very, very parallelizable. You take an image, you figure out what you need to do, and you kind of collapse your atoms into the right configuration. It is a little slow. The other thing you could do, if you're Dave Weiss and a few others have started to show this as well, is you can shuffle your atoms around using state-dependent tweezers or state-dependent lattices. You can push them around and essentially create a compactified set of atoms. You can do dynamic tweezers, and this has been done by a few different groups, including Cindy Riegel here and Anton Brawitz. So we actually started off thinking we were just going to do dynamic tweezers. How do you actually do this? Well, one of the things you do is you actually hire an engineer. Before you even start, when you work at a company, is you get to go and hire an engineer and you say, do everything, do all the software, do all the FPGA work. We didn't even have atoms at that point. The nice thing was, though, because all this work had been done beforehand, when we finally had atoms and were ready to do rearrangement, it worked essentially the first time it was tried. So you design a pipeline that takes images, that calculates movements, and then takes those movements and transforms them into pulses. Those pulses are very, very simple. They're actually just taking an acousto-optic deflector and just chirping its frequency. So one of the main things I'm going to show again and again is that we're really into RF, and we really want dynamic RF systems. And essentially the proliferation of dynamic RF systems is a key part of why we're building our system. We want everything to be controlled by RF. And I'll show that in the single qubit case as well. Okay, now we actually have to do optics as well. This is a very simple train that is going to do rearrangement. This design was finished in the first week of March 2020, which wasn't a great time to say, I'm going to go out and build an optical system. I think that Mickey took it upon himself and he said, well, if I'm stuck at home, he was going to go into the lab, literally grab a whole bunch of components that cost a whole lot of money, bring it home and build the system. Amazingly enough, it did happen. He built the system. It worked in his home. He brought it in. He installed it. It did not work at all. So he took it off the apparatus, rebuilt it in the lab, and then it worked. But he tried. So what was it like when we finally did it and actually could see on a camera that it actually produced light correctly? The first step was just seeing, could we trap atoms at all in this system? So forget about rearrangement, just say, can you just turn on light and trap atoms? Indeed, it happened like this. So we created a 2x2 array and we just started loading, and of course they popped up. Next step was, could you drag atoms around? We wanted to create arbitrary patterns. So we started off again as a startup, everything has to have our logo. So we did that. Here we added a filter so you can actually see what it's spelling. Otherwise, it's just single dots moving around and it's hard to see. And finally, can you drag and drop atoms inside a lattice or inside other tweets? This is really key. Again, we started off by just taking simple patterns of saying, what if we did 110 movements or something like that and moved every atom up, every atom down, every atom up, every atom down, and started using that as the signals which we could perform optimization. Very quickly, we found that there's lots of different things you can do. You can make your chirp faster. You can make it slower. You can play around with very complicated waveforms. Even with very simplistic waveforms, just linear, you can also even do better than just your normal kind of simple. And finally, you want to be able to do autonomous rearrangement. You want to take an image. You want to then take that information, calculate on the fly where you want to move the atoms to, and then perform that movement. We use the compression algorithm. Literally, it just compresses the atoms first into a diamond structure and then eventually into the actual square you want. We slowed it down a lot so that people actually see what's happening. Normally, it does not look like this. Normally, you get one image where they're all unrearranged, and then one image where they actually jump into rearrangement. Here we actually show that, or eventually I'll show that. Yeah. Right now it's not optimized, but I think it takes on the order of like 70 milliseconds. When we go and actually run circuits, we can actually shorten that significantly. So as you go, you can just wait a certain amount of time. So you kind of know the first time you load atoms, it's going to take a long time because there's a lot of movements. After that, it actually doesn't take that many movements. So you can kind of just shrink it down and just have a very, very quick rearrangement cycle so you can go back to running gates. So I talked a lot about mechanics and how you actually build systems with neutral atoms and 2D arrays. I want to kind of switch now and talk about quantum mechanics, how you actually take those systems and actually use them for actually forming a qubit. And here is where I'm going to talk about strontium. Strontium is a pretty ugly atom compared to other atoms. There's a lot of structure here. First and foremost, there's this dipole loud transition. It's very, very broad. It's very, very nice for imaging. and you can very, very quickly cool the atoms down to millikelvin with it. It has this narrower line transition, 7.5 kilohertz. I have a love-hate relationship with it. And finally, it has this clock transition. Very, very long-lived optical transition, whose natural line width has been measured, but it's on that order or so. In addition to that, because it is not a perfect system, it also decays, and you need repumps, so you need a whole bunch of lasers to actually control this system. But what I've started to show is 87 strontium. 87 strontium adds a whole bunch of MF levels. Let's plot them to the right. And these are the MF levels we're actually going to live in when we're doing actual quantum computing. We have the ground state singlet S naught with a spin of I equals 9/2. We have that ultra long-lived triple P naught with that same spin of I 9/2. And then we have a bunch of triple P1 levels. So we wanted to form a qubit. So first and foremost, we said, okay, how do we actually read out that qubit? We can actually perform an optical lattice clock almost. We can actually take one of those states and flip it up into the clock state. But then how do you actually perform rotations? That readout operation is pretty slow. And we realized, okay, well, let's actually just do a 2-photon transition, just like in ion systems. Okay, so now we talked about how we actually have this atom. Unfortunately, I just hid something under the bus, which is that fundamentally, that wasn't a qubit. There was tons and tons of levels, and it's really, really hard to talk to just two sets of, or two levels. Here we came up with a little funky trick. We actually add another laser beam, adding laser beams to our system, especially all the people who work in my company. So we added another laser beam that now pushes and essentially takes this degenerate ground state, or degenerate ladder, I should say, of ground states, and actually just rips it apart and pushes one of the levels really, really far away. The nice thing about this, and this is something that's, I think, a lot of papers are coming out with right now, pushing on a state that we are not ever populating. And that's a very, very cool way of actually using Stark shifts to give you control that you don't normally have. Don't push on the states that you do have population in, but push on states that you never have population. Okay, so obviously, we go and look in literature, and we actually find there was an experiment a long time ago with ytterbium where people started playing with single nuclear spins. But the question becomes, is a nuclear spin qubit actually stable? So let's talk about all the ways the nuclear spin qubit is not stable or could be not stable. And let's figure out if it's going to be a problem or not. So first is motional decoherence. Then we'll talk about scattering. And then a question that I think we asked ourselves a lot, which was just, why does everything in nature just not drive this super low frequency qubit? Some of us came from superconducting qubit systems where the qubit frequencies were many gigahertz. And we kind of got it drilled into our head that, you had to isolate a system like that. Now we were going to a qubit where the qubit splitting was about 2 kilohertz. So whatever we essentially shine light on that, why does it not actually just perform a qubit rotation? First and foremost, motional decoherence. Obviously, this is CU Boulder. June's in the audience. I made his name ever so slightly larger than Katori's right there. They came up with the idea of actually coming up with a magic wavelength. What this allows you to do is have different electronic states normally see different trap potentials, except at a magic wavelength, at which point it does not matter which electronic state you're at. And there's very, very little motional decoherence depending on how tightly you get that magic wavelength. And everywhere in the trap, the qubit frequency doesn't change. Okay, unfortunately, though, we're not talking about an optical transition. We're talking about different MF states in singlet S naught. So, of course, what you have to do is you Google for your favorite, essentially, paper talking about how you actually calculate polarizability. And you start to look into this and you say, well, what are all the things that are working in my favor? First off, I have j equals 0. So there's no vector in tensor shift. But unfortunately, because alkalis have this problem, you could say, well, is the scalar polarizability different? Luckily, it's not. And the reason why is because you're just so far detuned from the hyperfine structure. And when you do this, it turns out there's just, you're detuned by many, many, many terahertz, but you're actually comparing that to any shifts that would occur on the order of gigahertz. So now the question is scattering. You place your qubit, you're no longer worried about it moving back and forth in the trap. What about scattering? So there's two different kinds of scattering we should talk about. There's Rayleigh scattering. Rayleigh scattering, you might worry that it actually causes decoherence. Again, this work has been done here in Boulder. And it turns out here you would just have to care about the amplitudes. You care about the amplitudes of Rayleigh scattering, and you care about the amplitudes of Rayleigh scattering between your two qubit states, and if they're different or not. Again, and this is almost like a tick I now have, we don't have to worry about this because we're going to trap very, very far away, much larger, like a detuning much larger than the hyperfine structure. What about Raman scattering? Interestingly enough, Raman scattering, it's very, very similar idea. Again, here you're going to worry about essentially changing L, and you don't really have to worry about this if you're detuned farther than the hyperfine structure. So essentially what we've now talked about is a system where no matter where you are in the electromagnetic spectrum, as long as you're not near a resonance in your system, you're going to have, asymptotically speaking, a magic wavelength. And this is a very, very cool way of having a qubit with a neutral atom, because it means that once you have that qubit, you can transfer it to other traps, you can move it, you can do all these things that you might have gotten a little bit nervous of with an alkali element, because normally you'd have differential shifts and anything like that. But here the nuclear spin just doesn't care. Okay, so now the question is a little bit of a brain teaser, which is why do you not just drive transition all the time? And this, I would say, I have to go back, and I think that you go back and you write down, what is a two-photon transition? You write down the equations for it. You actually do math, and you get to this funny thing with this Clebsch-Gordon right there. That's CI. And amazingly enough, if you Google for it, you'll find a Clebsch-Gordon, a Clebsch-Gordon identity. And this identity, and I wrote this down to make sure I don't say it wrong, this identity shows that the sum of the product of the two Clebsch-Gordon coefficients is non-zero if and only if M1 equals M1 prime. Because we're using -9/2 and -7/2, that actually means it goes to 0, and that C over delta term actually disappears. And the next term that matters is this 1 over delta squared. And it turns out that this omega effective, that Rabi rate for driving transitions of your nuclear spin qubit, again, with my nervous tick, when you're farther away from the hyperfine splitting, keeps going down and down like 1 over delta squared. So as long as you are far away, you can't even drive this qubit. You can only drive it when you're within the hyperfine splitting of that upper state, of the intermediate states. Okay, so I've just described a qubit that essentially, it's hard to drive in some sense, and it has very, very little decoherence due to scattering or motional decoherence. What does this qubit kind of look like to me? It's kind of interesting because qubit with electromagnetic radiation, pretty much anywhere in the spectrum, except for those few tiny holes in the electromagnetic spectrum where there's resonances. You could put tons and tons of noise on that system, but because the qubit frequency is essentially made of nuclear spin, it just doesn't actually see that because it has very, very low sensitivity. So in my mind, the qubit just kind of hangs out in the atom. And this is really different than a lot of other qubits, I would argue. This qubit, you can move the atom around, you can push it, you can change its trapping, you can just do whatever you want with it, and it's just hanging out there. I like to say the qubit is inside the atom. Okay, but I didn't talk about how you actually read it out too much. Again, we can use this trick, essentially almost running an optical lattice clock, or this time an optical tweezer clock, to actually do this. We can shelve the atom. We can take one of those nuclear spin states, put it in a triple P9 on 461 light, and we can even do that twice and actually measure, both states of the qubit and see if we lost the atom or something like that. And here's where you can actually start doing quantum control. You can actually do this with different kinds of pulses, whether those are square pulses or Blackman pulses, and you can start trying to optimize how well you do this readout. Okay, so now the question is, how do you actually control these qubits? About being far away from the hyperfine splitting, let's now take lasers and put them right in the hyperfine splitting. We take a system where we have a light that is very, very nearly resonant with that triple P1. We split it up into two different components. We send both components through EOMs, multiple different AODs, and eventually combine them again to form 2D patterns. In fact, you can see the 2D pattern from our test setup. lot of RF is going into the system. You can, amazingly enough, do parallel addressing on a row or a column. And because you have independent control of all of the tones going in down to these AODs, within a column, you can choose any amplitude and any phase you want to drive the qubit. Use RF drives. And you can also define pulse length and advanced pulse shape with the EOMs. There's a few other reasons why we use EOMs, mostly having to do with how you actually turn on and off this interaction to make sure that the finite time of turning on AODs doesn't actually matter anymore. But amazingly enough, with 8 RF channels and 1 laser, with about essentially tens of nanowatts falling onto each atom, you can address an entire array of qubits without having to have a huge number of RF channels. You only need 8 RF channels. And we can also do this again, making pretty pictures like the NSF logo and stuff like that. This is our system that we actually use This is our system we actually use today in the lab, made with free space optics, built by quantum engineers at Atom. We also have a collaboration to try to turn this entire system into an integrated photonics approach, which uses the same kind of ideas of lithographically defined acousto-optic deflectors. Okay. So how do you actually use it in practice? You have all of these RF tones. You really need to build an automation or a feedback system such that you can actually talk to the atoms. You essentially want to be able to essentially perform the similar gate on every atom, but have arbitrary control, which means when those EOMs pulse, you can only define 1 pulse time, and the rest of your actual independent control has to be done with amplitude and phase. So if we go back to data, I think this is actually a little bit old data. You can start off with something where you're trying to oscillate between different levels. You can go through, build an automatic calibration routine, and you can make it look a little bit more uniform. Old data, what does it look like now with new data? First of all, you can have way more qubits than we used to have. And you can make these very, very uniform across these 110 qubits. And by the way, each one of these qubits is independently driven. And I think that that's not, there's lots of talk about how you could send global beams and things like that. That's very, very good. And there's lots of use cases for that. But here, each one of these qubits, actually in a, I think our rows and columns get switched, but we perform a column at a time and then cycle through for all 110. Okay, so we added a whole bunch of lasers to our systems. Obviously, nothing is ideal and nothing you add to your system is going to work perfectly. So what happens? First and foremost, the pusher beam, it starts interacting with the atom. You wanted to push away this MF equals 5/2 state, but of course, you're actually changing this qubit frequency ever so slightly. So we have a little bit of tuning, tune that around and actually try to minimize essentially action across all the qubit frequencies. Similarly, you want to choose that intermediate state to tuning. You have this, essentially you have to be within a few gigahertz. You have a range of essentially magnetic fields and choices to make, but you want to do it so that beam A and beam B have opposite sign Stark shifts. And then you actually want to set such that the pattern you're creating with beam A and the pattern you're creating with beam B has a fixed ratio so that you can actually have 0 Stark shift when you drive. Okay, so now that we can control the qubits, we should probably start understanding their properties and make sure everything we talked about before is actually true. So let's start off with, we drive each qubit independently. When we did this earlier in the summer, it was just 21 qubits. But we want to start with all the qubits in the ground state, and then we want to put some in the excited state, or essentially the up state of our qubit, and we want to start trying to measure what the T1 is. Obviously, it's pretty hard to measure. This is on a log scale. If we try to fit it and write down a number, it's a ridiculous number. And so the answer is much, much larger than we can possibly measure. If we compare this to other kinds of neutral atom qubits, we can see it's actually pretty different. Other kinds of neutral atom qubits, because they're in different F states, actually do have Raman scattering. And there you can actually see these qubits decay on the order of a few seconds, or maybe 1 second or so, depending on how deep a trap you're holding them in. Here we want to also understand this coherence. So we're Ramsey to measure T2 star. We're going to do pi/2. We're going to wait and do another pi/2. And amazingly enough, after you fix a whole bunch of RF bugs in your system, you see that at 1 millisecond, tens of milliseconds, 30, 300, 3,000 milliseconds, or 3 seconds, there's very, very little decay from your qubit. You can go out to about 21 seconds and we measure that or so. If we kind of, again, compare this to other neutral atom qubits, you can see it's actually doing a fair bit better. So I found one example where someone is very, very carefully tries a magic intensity. So they take their differential polarizabilities and they try to use, I don't think they used a magic magnetic field. I think they just used a magic intensity, but they tried to match the polarizability in their atom. And here you can see that they're out to about 160 milliseconds or so. So these nuclear spin qubits are quite special in some sense. Obviously, we wanted to understand, what is not just T2 star, but what is T2. We started playing around with this, and we very quickly, in some sense, gave up. We added 1 echo pulse, and we went out to about 40 seconds, and we saw still some decoherence. We probably understand where that decoherence is coming from, and we realized that it probably wasn't worth trying to go to larger and larger times, just because at the end of the day, these are single qubit statistics. So if you want to perform this measurement and you want to look at a single atom basis, this is averaged over all the qubits. We also have plots of this where every single qubit is measured. If you want hundreds of shots of this, every shot costs 40-something seconds. So it takes an incredibly long time to get this data. OK, so now what do we do with these qubits? Well, first off, we're a quantum computing company, so we have to come up with something named with Q. So we have our quantum language called Klingon with a Q. This allows us to write down gates. We can write it in the Klingon language. We can write in Qiskit and have that actually go through and compile down. And then we have an orchestrator that turns this into pulses. What can you actually do with a system like this when you have neutral atoms? You can start essentially programming gates. So here we show arbitrary gates performed on each of these atoms in the column simultaneously. And at every point, we're forming a different gate on the atoms. Of course, we don't want to just perform Rabi's and things like that. We want to do robust phase estimation to actually perform calibration of our gates. We want to do randomized benchmarking and keep making that randomized benchmarking look better and better. And even want to do gate set tomography and things like that to actually understand where the errors in. And amazingly enough, eventually we want to do pulse shaping. All of this is without any pulse shaping of any kind. These nuclear spin qubits are just very, very forgiving. So we want to do pulse shaping. We want to try faster gates, composite pulsing, and things like that. OK. Now the question becomes, we have a whole bunch of individual qubits. They have very, very good coherence times, but they're very, very far apart from each other. So how do you actually get them to talk to each other? Here we use Rydberg states. Rydberg states are kind of nice in the sense where you can go into and out of them fairly quickly. That's actually kind of the point. You have to go into and out of them fairly quickly. But their interaction is quite large. So even though the atoms are, say, 3.5 to 4 microns apart, you can have many tens of megahertz of interactions between them. This allows you to actually start having atoms in different sites and tweezers talk to each other. Many groups across the country or across the world now have actually performed really interesting high fidelity gates, whether that's in alkalis or in the last one where they're doing entanglement in alkaline earth elements. So how do we do it? We spent this entire time talking about this chain of AODs and EOMs down here. We essentially just turn one of them off. Here we just take one of the photons. We use it to go bridge to the intermediate state of triple P1, which is a very nice intermediate state to go to because it has very, very low. And then we add another photon at 317 nanometers. We can do this with any number of qubits we want. Normally, we want to just do it with 2 qubits, let's say. So we shine on the red light, we shine on the UV light, and we can start actually looking around for Rydberg states. Here we can do this, and we see the Rydberg spectra. Unfortunately, we're going to magnetically sensitive levels, but at the same time, so fast, we can just drive really fast, and we're OK with that. Now, we want to actually do all the things we did with our doing them with our 2 qubit gates. We get Rabi. We can realize that we need to optimize phase noise and do better. This is us optimizing phase noise, I think, on just one laser. We're doing the other laser, or done the other laser. We can start looking at spin echoes and Ramseys and things like that. And I'm happy to say gate fidelity is coming soon. OK, but the question now becomes, what can we do in the future? So I'm actually going to highlight this work by Emmanuel Andres, where they're actually doing a few things a bit different than us. So first and foremost, they're working at a much faster Rabi frequency. Our Rabi frequency is almost about 1.5 megahertz. And they're actually using a laser that's actually a bit quieter than ours as well. And they're performing many, many oscillations in the ground to Rydberg space, and they're doing it at very high fidelity, actually. So I would say that the thing to take away from this, in addition to the numbers they're talking about, is how you actually build the next generation systems. So first, I would say start with an inherently quiet laser, even quieter than the laser they're using. Utilize very, very fast Rabi frequencies if you can. You have to turn on and off the light, which is quite difficult. And fundamentally, you have to also make sure that other interactions with the system, whether that's photoionization and trapping, are compatible with utilizing all that coherence. So you have to be pretty careful about that. So I only have a few more slides left. So I wanted to give a few final thoughts. I wanted to show this because it keeps getting flashed up again and again and again. And to me, it's actually really exciting when a competitor shows this. This is a plot of entanglement fidelity, trapped ions and superconductors and neutral atoms. And what's amazing to me about this plot, again, created by a competitor of ours, is that right around the time a wave of interest in development and investors started in neutral atom quantum computing, things started getting really good. People started coming up with really cool ideas, and things are getting better and better and better. In addition to that, I would say the system size of neutral atoms is getting larger and larger and larger. And I would say I would rather be on the red slope than other slopes. But I think that's a point of contention, I guess. Okay, so finally, I'll give one last pitch of neutral atoms and try to explain, be interested in starting the company. At the end of the day, it seems like you need quantum error correction. And if you need quantum error correction and no one comes up with this amazing new kind of quantum error correction, you're going to need hundreds of thousands or millions of qubits. So what does 1 million qubits look like for different technologies? As far as I can tell, this is like the Shai Hulud of a dilution refrigerator. It's like eating this person, but it's a very, very large and very, very complicated system that I assume doesn't exist today, or they're keeping very, very secret. For ions, the systems look a little bit cleaner, but they're still fairly complicated. You're essentially building many, many setups with many, many ions, like 1,000 ions, which I don't know if exists today, but it's potentially going to exist in the future. And you're coupling about 1,000 of these units together in a switch that has some very awesome properties, I guess. So it's quite difficult, actually, I would say, to get to 1 million. And I would say that was one of the main reasons why I started getting kind of pessimistic about quantum computing in general. That wasn't until I started thinking about what people and what people could do. So does a path to 1 million look like? A 3D array of atoms with 100 by 100 by 100. I think just recently I said this to someone and they very quickly told me that's 1 million. With about 3 micron spacing per atom. If you wanted, I'm going to pick this. Not that we've done this calculation, obviously. If you pick this trap depth at 20 megahertz and you build a system of cavities with a finesse about 3,000, which is pretty low, actually, and you loaded 16 atoms every second. We load way, way more than 16 atoms every second, but of course, it takes us about 100 milliseconds to do that. But when you want to work with a system like this, you're probably going to want to load, then spend 90% of your time computing, load, spend 90% of your time computing. And if you had a vacuum lifetime just 10x better than the best reported neutral atom lifetime, you would need about 1 microwatt per atom for 1 qubit gates with these nuclear spin qubits, and global beams for everything else. Some of them you do have to get to almost 8 watts to actually make this all work with the Rabi frequencies you want. But the question becomes, where is the real bottleneck? And I would argue the real bottleneck, and at least previous in my mind, was how much trapping laser power you need. And amazingly enough, you need 2 watts. All you need is 2 watts of laser power to create 1 million trap sites suitable for trapping the atoms. You're actually creating many, many more trap sites than that. But if you place the atoms far enough away such that you can actually resolve those atoms, it takes about 2 watts. So one of the things that got me started with atom computing wasn't that I was an optimist, it was that I was a little bit of a pessimist. And I think this made me happy, let's say. So with that, this is atom computing. This picture was taken actually in August of just a few months ago. It doesn't include any of the new people who have joined, who are working in the Boulder office, and I apologize for that if you're watching. But eventually we'll take another picture. And with that, I want to thank you. I would say it's the pusher beam. So the way we actually isolate these actual nuclear spins, I think that there's a little, I'll hesitate a little bit because pulse shaping will also fix that. But in general, the ultimate limitation for a scheme like this is the pusher beam, is just leakage that you're actually driving by having a detuned transition out of the qubit subspace. I would say once again, you're limited to the pusher beam. So I will say the pusher beam itself does cause some tiny amount of heating. It hasn't been, so it's on the order of, I think, a 1/e time of like 1 or 2 seconds or something like that. One of the ways you could fix that is if we essentially automated the kind of lambda/4 that's adjusting the polarization of that pusher beam. But again, 1 or 2 seconds didn't really seem like it was a big deal. So I think it's the pusher beam is the ultimate limitation for this. Next, after that, say you got rid of the pusher beam, maybe you moved to an atom that doesn't need a pusher beam. I would start to worry a lot about Stark shifts of the actual Raman beams themselves. You can try to build actual like composite pulse sequences that maybe get you up to the full lifetime. And once you do that, I would say it's just going to be scattering from the Raman beams themselves. And there you're going to have to just balance Rabi rates versus detunings and things like that. It was the, what is the limitation for this Rabi oscillations? That's native gate, actually. It's native gate RB. Oh, sorry. He asked, is it native gate RB or is it Clifford gate RB? So that was native gate RB. I don't know the Clifford gate RB off the top of my head. So. They kind of spread around. So this data was taken in August. So for example, our data used to kind of look like this in August, and now it looks like this. But that was about, there were some qubits over 99%, some qubits at 99%, stuff like that. Per native gate. Sorry, I don't know where. Yeah. Yeah. So the Ramsey data is, sorry, where is the Ramsey data? The Ramsey data is post-selected for keeping an atom. So currently our vacuum lifetime is about 60 seconds. So that's another reason why it was really difficult to go long times. Yeah. So we would run essentially, I think when we did this, low number statistics are actually really weird. So when you actually like have just a very few numbers, that you probably notice, when you have very few numbers of atoms, you can actually sit there and take many measurements. So it's not like we would take one circuit and then start from scratch. We take one circuit and then run that circuit like 4 or 5 times, even though it was out to like 30 or 40 seconds and our one relief time was 60 seconds. Yeah. Sorry, where is that? I would say that 2 things would be better. So one is not using a pusher beam. So that's first and foremost. That's also going to increase essentially ability for you to just drive the gates faster. So we're trying to go to megahertz level. Whereas with Strontium, you're both using a weaker transition to actually do this, and you're worrying about the pusher beam. Whereas you just as you essentially drive faster and faster, your leakage would go up. Of course, the pusher would help to have more than about 5 milliwatts in the pusher beam. If you had, say, 50 milliwatts or even like more than that, you could actually use the pusher beam really, really efficiently. But it doesn't seem like it's going to be the end all be all. So it doesn't really seem like it's worth pushing up the power. Yes. So if you use AODs, you need to have them both be local addressing. If you want to not have a frequency shift between atoms that are essentially both illuminated. Yeah, yeah. I mean, you could try to do some wavefront shaping before the AOD and maybe, yeah. Yeah. So there's been work by Dave Weiss on using essentially two beams coming 90 degrees to spectre each other. And so we have ways we've kind of thought of using essentially AODs that are coming from two 90 degree directions, which allow you to essentially address every atom in your 3D array. And if I'll say the work being done by University of Washington, Sandia National Labs, if that works, I think you can also take that system and that will actually work really, really nicely for 3D addressing. Yeah, so when we're doing, I mean, we've shown blockaded oscillations, and we can also measure that. I think we're not ready to talk about our 2-qubit gate fidelity yet, but yes. Yeah, so I mean, I think that what we're doing right now with 1.5 or so megahertz of Rabi rate, I definitely think we want to get higher than that. I think that a combination of a tighter UV beam and also an inherently quieter laser. So the way we're actually creating our UV light is a little bit noisier than the system over here. And also I would say that one of the main nice things about this system is that they just have 7 megahertz of Rabi rate. It's about like 8 watts. I mean, I think that you have to, I think that with pulse shaping, I think that if you're worried about like nuclear spins and how you actually like choose one versus the other, yeah, I think we've spent a lot of time thinking about like pulse shaping and how we would try to actually do that. Just because like what we do a lot of the time is we're actually trying to separate out driving 2 levels that are on the order of like 100 or 200 megahertz apart. Yeah, so there's actually now 4 different new techniques, including atom computing. There's Pascal, cold quanta, and QEra. I think some of those are focused on, you could call them quantum simulators or machines that are kind of more geared towards solving like a very specific kind of problem. And the other ones that are kind of focused on gate-based approaches, I think are these hyperfine qubits, although you'd have to ask them. So. I have a lot of. There's a lot. Hi.
Weicker?
Oh, hi. I think we've met before a long, long time ago.
Long
Oh,
time
yeah.
ago in Georgia, if I remember correctly. It was a workshop